Lately, I've been pursuing an idea. It's nothing so specific as a single conjecture that I could turn into a definite theorem. It's at the notion for a notion stage. The theme I'm trying to develop is that, perhaps, quantum mechanics is the simplest, most symmetric and featureless theory of probabilities that is consistent with the non-existence of hidden variables. When I first learned quantum mechanics in college, nothing about it was simple. And now that I'm teaching it to college students myself, I'm pretty sure they don't find it very simple either. Sorry, but maybe this is an unhappy accident of history. Maybe there's another perspective on the theory, another language in which to express it, that brings the essence closer to the surface. Here's the gist. If I shake a pair of dice in this backgammon cup and roll them onto the board, you don't know what numbers came up, do you? But there is some fact of the matter about what happened, isn't there? I could resolve your uncertainty simply by revealing that fact. Now, in quantum mechanics, we talk a lot about uncertainty. If, say, I prepare an electron very carefully so that I can be completely confident of where it will be when I measure its location, I necessarily forsake the ability to predict what will happen if I try instead to measure how it is moving. And likewise, if I prepare an electron so that I am completely confident of what will happen if I measure its momentum, I will be completely uncertain necessarily about what might happen should I try to measure its position instead. The big question: is quantum uncertainty just like your uncertainty about that dice roll? Are we just tripping over our own feet when we try to measure something so tiny as an electron? Might there be hidden gears of some kind within the electron, such that if we could only find how those gears were aligned, we could predict exactly what the electron would do in any circumstance? Uncertainty principle be damned. Most intriguingly, no. The takeaway message of a whole lot of experimental and theoretical work is that nature is more strange than that. Quantum uncertainties must arise from a source that is not mere ignorance of hidden properties within the things we study. The hypothesis that hidden variables are lurking behind the scenes implies relations between the probabilities for what might happen in different experiments. But if we try to gamble in accord with those relationships, we find that nature surprises us and steps outside them. We are ignorant, it seems, not because the facts are concealed, but because they have yet to come into being. All this is not obvious from the way we usually introduce quantum mechanics. One must tease it out of the mathematics, and so the textbooks bury it many chapters in, even though the idea that nature might be vital and creative in this way is a sufficiently dramatic idea that it seems a good place for the story to begin. Retelling the story of quantum mechanics in this way will require making precise what we mean by the most symmetrical theory. In turn, this seems to require solving a thorny mathematical problem known as the seek existence question. But that's a topic for another day.